Hello, and greetings to any. Happy holy days and a Merry Christmas and a Happy New Year with that all approaching. If I don't put out another video before then, it's been a while since I've posted anything. And this is that test bed circuit that I described building previously. The only difference right now is I'm discharging this cap through this coil now through a BJT, and I'll also use a MOSFET. Whereas when I gathered the data, which I'll share in a little bit, I also used the discharge through a solid state, optoisolated solid state relay. So as we discussed in the previous video, I believe that the advantage with the discharging through the solid state relay, the SSR, is that now everything's opto-isolated. Everything on this side is one side, everything on that side is the other side. The disadvantage is that the SSR is tripped by an LED, and the maximal speed is, per the specifications for these Comus AC37s, is around 200 microseconds, and it seems in this application to be around 100 microseconds. However, this should be able to go down to a microsecond, and I think, or at least a few microseconds, and a MOSFET should be able to go down to nanoseconds. So this is faster, but the disadvantage, if you want to call it that, is that you connect the ground on the Arduino to the emitter here. This is an NPN. I believe it's I want to say a tip 42, I'd have to check. Tip 42C, I believe, 100 volts. And so now you have this line going to the ground. There's an electrical connection back to here, hence to there. And so, it's not all opto-isolated. It practically shouldn't make a difference, but since I don't really know what I'm doing, it was nice to gather all the data with it opto-isolated. So, I'll share that in a moment, but I'll just talk through this circuit a little more. Well, before I even get to that, I learned something that for me was quite interesting just really a few days ago, and I was reading just on a tangentially related topic, and what the person said was, someone was trying to do something fast with the Arduino, and a person commented, well, you want to look at direct port manipulation, because when you use the function called direct write, that uses 10 to 12 clock cycles. So if we go, this is just the built-in blink example, and you see that when it turns on the LED, it does so by saying digital write, LED high, then turns it off, digital write, LED low. And each time you use that, it uses 12 clock cycles. Now then, the crystal oscillator in this Arduino Uno is 16 megahertz. However, out of the box, the maximal speed this runs at is 1 megahertz. You can try to one can change that and get the full power to 16 megahertz, but it's it's like assembly language code and whatnot. So there is, if you have a reason to do it, go ahead and do it, but first figure out what you're trying to do. But we can do some math, and if it's 1 megahertz out of the box, and if you use 10 clock cycles, then the fastest you could be going would be 100 kilohertz, which coincidentally enough, everything stopped improving at 100 microsecond pulse, which would be 100 kilohertz. So I'll just show you there real quick. There's an instructable on this topic that I found, and what was nice is he put it on an oscilloscope and showed the difference. So here we have this instructable Arduino and port manipulation. And it's going down through here, and so on and so forth. And so we see with this code, he just, turns pin 0 high, turns them all high, but pin 0 high, and then turns pin 0 low with no delay between the two. And on the scope, he got 14.983 kilohertz. So a little faster than 10 kilohertz, but maybe like a 75 microsecond pulse, and then you're done. Even though you have a 1 megahertz, the oscillator can go at 1 megahertz. Now, here with direct port manipulation, where is it? He's getting 1.14 megahertz by just going high and then low. So here would be an example of the blink program rewritten with direct port manipulation. And that's turning pin 13 high and low, and pin 12 high and low, and then pin 11 high and low. And so then I rewrote the cap discharge as a direct port, and that's what this data is. That's what this code is. I need to ungray out some of this when we get going. So now it's using direct port manipulation, so I'm more confident that I can get down to at least 2 or 3 microseconds instead of 70 or 80 where I was topping off before. So the other offshoot of that realization is I will finally buy myself for Christmas a decent entry-level desktop oscilloscope. And I got some advice from someone who uses one of those for a living, and so I'm looking forward to purchasing that. I purchased that little DSO Nano that's like $100. The screen's like the size of a postage stamp. It's useless to me. But if I had had a scope, I would have known what was going on when I was programming that with the digital write and thinking I'm at 10 microseconds when I was still just sitting at 80 microseconds because the digital write call was just churning through a dozen clock cycles. So now there's that. Now even with that, I'm kind of seeing similar results with this coil as I was seeing previously. And I will, as I said, in a moment share that data. And it turned out to be a bit of a disaster. I won't say a disaster, it was a headache. This redfish meter, and they've subsequently gone out of business, and I'm starting to wonder if maybe I know why now. But you can link this thing to your phone through Bluetooth, and that's really nice because then you can do data logging straight to your phone, and then your phone's supposed to be able to export the file to an Excel spreadsheet, and then you have it on the computer. It would not export from the phone to the computer. The application just crashed every time. So I can't remember how many, if like either 100 or 300 data points, and I had to take them and type them all in by hand. And even then it's not as straightforward as it sounds, because what you're doing is you're pulsing this coil through the cap at, let's say 20,000 microseconds, and you're seeing what shows up here. Well, before we even get there, let's just talk through this with it running, like 1 second at each step, and show you what's going on. Okay, so to start with, we have the meter going to here, and we'll run this at 3 volts. And let's talk through this. So this is saying pin 13 goes high. Here's pin 13. And that's turning this on, and then you see it goes over here, the same signal goes over here, and it turns this SSR on. And what do those do? Well, one makes a line from the positive to here, and that's that switch. The other makes a line from the negative to there, and that's that switch. So the positive and negative from your power supply are made and broken when pin 13 goes high and then low. I keep getting interrupted now. I'm not sure where we left off. But here's what we're going to talk about. So this line here turns pin 13 high. Cap is just sitting there. Then pin 12 goes high. That's what this is. This is pin 12, as discussed previously. Before is an SSR. Now it's a BJT, and I'm also going to do it with MOSFET. When pin 12 goes high, so now there's a switch made here, and you can see the positive goes into the collector, to the emitter, round and round and round, to the negative. So the cap now discharges through the coil. There is a backwards diode coming off of this positive leg going to the negative of this cap. The negative of the cap is connected to here, which is the positive of this cap. So again, those two are reversed, and that's a buck boost DC voltage converter. So if we let's just turn this on for a moment. Oh, come on. You know, right now I have the meter on this cap, and so what do we see? We see charge up to 3, pin 12. Oh golly, it's broken. Okay, a wire, focus, a wire came loose. So pin 13 high charged, pin 12 high discharged. Now we move the meter to here. This is where we're gathering the induction. And so when pin 12 went high, there was a spike that gets rectified into that other cap. And then we have this where pins 11 and 10 go high and then go low. So there's pin 11. Pin 10 right now is not doing anything, and I'll explain that later. So pin 11 has a line from the positive of this cap to this SSR to the negative. So when pin 11 goes high, this cap discharges back down to 0. So we have it on that cap now. So 0.324 volts down to 0. So now just a few more things, and we're done explaining this. This is a for loop. So right now we're pulsing it once and then discharging that. But we can set this, what I did was set it to 25. So now we gather 25 spikes and then we discharge. Now, where's the action going on? The action is going on when you discharge the cap. So we're going to get rid of that delay for a second, and we're going to put all these down to like a millisecond or something like that. That's all. It needs less than that to charge the cap. And so you'll cycle through those 25, in a fraction of a second. And you see what voltage ends up in this cap. Should I do that? I'll do that once. So we've gotten rid of the lengthy 1 second delay, and now the cap will discharge for on time. And so right here we're setting on time equal to 20,000. So 20,000 microseconds, which is then 20 milliseconds. And it'll go through this 25 times, and we'll see what shows up in the cap. And I've turned it up to 10 volts, and it's going to about 5 volts is what we're seeing there. So the final part of this is, after we've done that once at 20,000, then down here we set on time equal to on time minus 100. So now the next time through it'll be 19,900 and then 19,800, and we see what shows up in this cap each time. So it's a frequency sweep. And then, and I'll show you that data. It's interesting. And then we're going to look at what happens doing the exact same thing, what happens with this cap each time. And that's also interesting. So the final thing, and then I'll just go to the data, but just so that you know what was done. So that's the data that we'll be going over in a moment. The light is kind of annoying. So why do I have this other switch here? Now that's for when you want to do something different. Let's say instead of wanting to discharge this cap to 0, you wanted to take this cap and discharge it back to the source. So if you're at 10 volts, it would be, you pulse it 20 times and you see maybe it goes to 11 volts. And then you discharge it back here. And what you do is you put in a cap there. And once this cap has been filled, you disconnect the power. I'll leave it on for now, but you disconnect the power. Now what's happening? Now the machine is running off of this cap. So this is a 1000 UF cap, this is a 10 UF, this is a 100 UF. So just to kind of give the ballpark. So that's why you would have the second switch there. You would take the positive and shoot it back to the positive here. You would take the negative and shoot it back to the negative here. So you're shooting it back to source at 10 volts, and you're seeing how much you're going above source. So if you had something that was running itself or was right at 100% efficient, since this is 100 UF and this is 1000, this is 10 times bigger. So if this went from 10 to 11 and this went from 10 to 9.9, then that would be 100% efficient. So I haven't seen 100% efficient. I've seen like 80% efficient. I've even seen 90% efficient occasionally, which is, for me, that's really cool because it's hard to find a DC-DC converter that's better than 85% efficient. But when you fiddle around with this coil, that's what I was seeing. So that's sort of like the acid test of, where are you? But irregardless of that, let's just go back to when you're pulsing it 25 times each. How does this thing behave at different cycles per second? How does this thing behave at different cycles per second? And it's really the pulse length. So let's go to the spreadsheet and look at that. So if we recall, this was from a previous video, just gathering the baseline data for that big coil, the inductance, resistance, and what capacitor we were using, and then calculating the tau time and the resonant frequency, the calculated ones for that, and then also later on in the spreadsheet I can put in what I'm most interested in is the skin effective resistance at those different pulse rates. And here, and again, I had to key this in by hand, all 300, and it was not fun. But furthermore, I am fairly certain, because you have the on time when you're at 30,000 going through for 25 times versus when you're at 10,000 going through 25 times is different. Yet the sample, you can only sample it, say, once every half second. And so there's a spacer of 0, but what I'm saying is, if this were genetics, there's probably a frame shift mutation or two in here where, this should be here instead of here, and then everything after that is going to look ugly. So it was a darn shame that didn't import right. But we can still just kind of look at it. And so let's just graph this. So again, we're running at 10 volts. There's 25 spikes, and we're seeing how much voltage shows up in that 100 UF cap that we're gathering from the inductive spike. And we're doing that with a duty cycle 50%, 30,000 microseconds on, 30,000 off, 29,900 on, 29,900 off, so on and so forth. And what the graph looks like, come on, what the graph looks like is that. So that's kind of interesting, isn't it? For most of the time, it doesn't even get back to the starting voltage. However, we see there's a spike there. There was a spike there, smaller. Then a big spike. And then this I don't think is artifact. And then it starts over. Boom. And see, this one's a little higher than there, and this one's a little higher than there. It's not dramatic, and I think that's, I don't know, maybe because of how much resonance, I'm sorry, how much inductance the coil has. But this is your primary resonance. So this is from 30,000 going down to 100. And this is at around, I'd have to look at it, well, we can see it, 13.18. That's at 1400 microseconds. So 1.4 milliseconds is that spike. And then it starts to go down again, like it did there. Actually, it doesn't follow that exactly, but it does start to go down. So what exactly are we looking at? I don't exactly know. I do think you want to be careful that this is the spike being gathered into that cap that's gathering the inductive spike. So this is not, I said before, this is a primary resonance. I shouldn't have said that. This is the best voltage you're getting out at that cap, but the resonance is between the other cap and the coil, right? I mean, there's that cap and that coil, and then this is just gathering, and we're seeing that there's things that kind of look like a resonance, and then these look like harmonics to me or something. It almost looks like, you'd call it like a third and a fifth or something like that. But be that as it may, there's this behavior, although this isn't the resonance, but there are places here where this does really well. Now, so now we've put in what the voltage ends up at in that orange drop cap that's being discharged into the coil. So this is the actual LC tank circuit. That's the C of the LC. And you can see it discharges to 2.063 there at 30,000. And that's it at 29,900. And I mean, I would just say that remember that cap is being discharged 25 times, and you're only seeing it after the 25th one. So then, the question is, well, what did it discharge to at the 20th one, and at the 15th, and at the first one? And I haven't gone through all 25, but it looks about the same, at 1 and at 2 as it does at 25. So I'm pretty sure that it's about the same through all 25. So again, there, and then it starts not discharging as much. So that's kind of nice. And here it gets out, it's only discharging less than halfway. Recall the input voltage is 10, and it's only discharging to 5.1. And now even 5.322. Now it starts going the other way. And going to here, and going to here. Rut-roll. There we're at negative 6.55. As we see here, discharges to negative 6.55. And then negative 1.2. And you kind of think, well, I thought a cap only discharges to 0. But, this one goes to 11. And you think, well, maybe that's just, some kind of sampling thing. Then you go on, and Look at this. Look at that. Negative 6, no, that's negative 5. Where's the best one? Negative 6.17. Negative 6.17 volts. And then it starts going back up again. I should try to put in the rest of the data. I just gave up. This was like 600, nearly 600 times I had to key this in. So I stopped there at 1100. But let's graph this now and look at what this looks like. So insert chart and finish. Okay, isn't that interesting? This is the behavior of the discharge cap. Now then, this I would now say, or no, I would not. This I would now say is your primary resonance. And it's, no, I'd have to, no. I would say this is your primary resonance. That's the way I read it. Because see, now we're talking about the actual LC tank circuit. We're not talking about that cap that's just gathering stuff. This is the cap and the inductor. And when it's going negative is when all of that current ends up on the other side. So it's sloshing back and forth between the inductor and the cap. And when it sloshes back from the inductor, it's going the other direction. That's why you get, recall the backwards diode. That's why you get stuff going in. And that's what we see there. And this is what I would say is the primary resonance. And where is that at? And there it is. Negative, it flipped negative with an input voltage of 10. It flipped negative to 8.21 volts when, with the 50% duty cycle, this was 3,700 microseconds. Now, if we go back here, we calculated the resonant frequency as 3 microseconds. So it's not that far off. So that is our experimentally what we see. And again, there might have been a frame shift, so this might be like at 3,500 or 3,400. And, you know, there might be different inductance and capacitance in the circuit that I didn't measure correctly, you know, that's not showing up on the instrument. But we're in the ballpark for what we calculated for the resonant frequency. Now then, in a moment, we're going to look at both of these. However, I don't know how well they're matched up. And it's a darn shame because I really wanted to see that really clearly, and I can't now. But I'll probably, like, at certain points where I'm interested, like around that 8.21, look at both of these. But before we get to that, let's just talk about this for a minute. So you think, you know, oh, darn. Now, instead of, you know, charging from 0 to 10, you have to charge from negative 8.21 to 10. That's going to be terrible. However, recall that that was that orange drop cap. That's not a polarizable cap. So in other words, you're at negative 8.21 here. You know, it was at 10 and then it went to negative 8.21. You flip that cap over, now you're at 8.21. And so you only need to put 18% of the energy, 18% of the charge back in to bring it back up to 10. So that's the first thing, is that, and you can do even better than that with the smaller cap. This has to do with the Q factor and the resistance present in the circuit. So, you know, if you like soldered the connections, and if you used a smaller cap or whatnot, you could probably get that to -9. If you had a negative resistance element, I don't know how those things really work, but germanium diodes, germanium diodes, or things like that, and you understood what you were doing, that might go to more than -10, and recall the input voltage is 10. But you could get that. This is good enough, right? This is, flip that over, and you're back to 8.21, and you only have to put in 18%, less than 18%, to get back to 10. Now, does that mean that this is then an over unity DC-DC converter? Probably not. I'm going to have to look at it. But the other interesting point is when you go really fast, and this thing is only discharging from like 9 to 9.8, and you still get some, again, these don't match up well, and I apologize about that, but you still get, so those are the two places where you're going to have high efficiency. Either, if you took it at that resonant frequency and then flip the cap, that would be high efficiency, or if you just flat out go as fast as you can. And so we'll leave that there. But, forget about the DC-DC converter for a minute. You have a way of pulsing a coil and then getting back to your starting voltage, only using 18% of the charge that you normally would. So you can think, what else might one do with that? Well, you think of, like, say, an incandescent light bulb. That's plugged into AC. It's going positive, negative, positive, negative. So, there you wouldn't even flip the cap over. You just flip the power supply, go 10, -10, 10, -10. And that's similar to how an incandescent light bulb is coming in off the mains power. Now, a traditional incandescent light bulb is going to have a resistance of approximately 100 ohms once fully lit. And resistance, again, damps this out. And so instead of going, where is it, -8, wherever the heck it is, -8.21, maybe it goes -3. So now you can have lighting for 70% of the power that you normally would. I'm not sure what the lighting is on a fluorescent bulb. Actually, there's something funny there. I was curious and I typed in, what is the resistance of a fluorescent bulb? And so, there's this, and then we get to the third thing. Fluorescent tubes have negative resistance characteristics. So, and evidently the ballast on the bulb is to deal with that. So there are a couple different forms of negative resistance, and I'm not an expert on that, but depending on the type of the negative resistance, it would be really interesting to put a fluorescent bulb in series with this, wouldn't it, once you got rid of the ballast. Another thing you could do is an LED. The LEDs don't have a great deal of resistance. And I'll give you another little secret. If you take a cap, discharge it through a coil, through a conducting diode, you're going to end up there minus the minus 0.6 volts from the diode, if it's a silicon diode. And that will occur at whatever frequency you want to go at. Maybe it wouldn't go if it was too fast. But what I'm saying is, here we're using the timing so that the current all ends up, negative or positive. Here, negative. When you have the diode in place, it's a one-way valve, and so it can only end up at this point, except for, again, the 0.6 voltage drop across the silicon diode, or 0.3 or 0.2 with a germanium diode. And so you could take a diode and put it in series, a light emitting diode now, not a regular rectifying. Put a light emitting diode. Now you can pulse it at whatever you want, and you're going to get back 75% of your power. So let's just think that through for a minute. You would have, now, I guess with like film, it's, I don't know, 100 frames per second or 70 frames per second or whatever. If you're out here, at like 300, times per second on and off, or whatever, maybe that's a lot faster, but it's a lot faster than 100. 1,000 would be a kilohertz, so you're like going 1,000 times a second. So in other words, power on and then off, since it's a 50% duty cycle. So right there, you save half of your charge, as opposed to just putting direct current through the LED, but your eye perceives it as just a constant light. Then you could save another 75% because it would flip negative, and then you flip it over and you only have to charge back, either, from there or from negative 7.5 or whatever. So in other words, all LED lighting would be 8 times more efficient. So I have this little Phoenix light that I really like, and it's great for when you're building stuff and you're trying to see where the lines are going. And you put this thing on low, and it'll last for seemingly forever on low. And had a little coil there, and this was, a little bit longer. Now it'll last 8 times as long. You'd leave it on high for hours without the battery going dead. So now you can get light for, a quarter the cost. So that's kind of neat. What else might you do? Well, instead of, if you didn't want light, maybe you want heat. And so if you pulse a coil with a capacitor, and you do it really fast, and it's a big pulse, and then you stick an iron core in, there are eddy currents that go through that iron core as the magnetic domains switch back and forth from one side to the other. And that is registered as heat. So here is a site out of England called RMC Cybernetics, and they're doing just that. They're taking some large gaps at high voltage, and they're discharging it into this coil. And the circuit that they're using is what's called a Royce oscillator, and they're saying it has the advantages of simplicity and self-resonant operation. And here is the circuit. I haven't looked at it in depth, but that's a circuit running in resonance, and it's a cap pulsing into a coil, an LC circuit. Now here's the interesting thing, is what they're mentioning here, is in this picture, they're putting that screwdriver in, and it's glowing near red hot. And with the induction coil shown here in that picture, the circuit draws about 5 amps from a 15-volt supply. So if we do a little math, 5 amps, 15 volts, that's 75 watts. This is drawing 75 watts. And in 30 seconds, the screwdriver is glowing red hot. Now I have a space heater that draws 1500 watts, and I don't think it has that degree of heat and that mass of heat. So what I'm saying there is, if you apply this then to induction heating, you could heat a room and possibly your house with 75 watts. Because I imagine there are ways to optimize how much mass you're getting heated there. I mean, they're just taking a screwdriver and sticking it in. The other thing that they mentioned about this is, well, the copper tubing is going to glow hot, and so one of the things that you want to do is you want to take, this will be hollow copper tubing for the coil, you want to take water and run it through there to keep the coil from overheating and potentially melting like that. I mean, I imagine you're not, well, I mean, iron doesn't turn that color without being pretty darn hot. So you run water through. Now, what do you have? I mean, now you have a space heater. You have that water, you just run that into a radiator there, and now you have your space heater. And again, depending on how much heat you're actually getting out of that, maybe you could even heat more than, a small room. And that's 75 watts. So that's another application of this. And they sell kits for building this. I don't want to talk this up too much. I mean, for one, because I haven't built it yet. And there's a little bit of a funny story. I stumbled across these guys like, it feels like 10 years ago or whatever. Now they have like whole like pre-built kits for it as well, so you wouldn't even need to do much work. I mean, the real work would be turning the thing into a heater and, having the bells and whistles if it toppled over that shuts off. But I remember seeing this and I just commented, I was like, that's amazing. What do you guys think the efficiency of that thing is? And it was sort of like, if you've seen the movie The Fugitive with Harrison Ford, and I can't remember what his name was in the movie, but there was Tommy Lee Jones was the agent trying to find him because he'd escaped. He escaped from jail. He was falsely accused, and they go into a hospital, and they're thinking, well, maybe we can get some information here. And they see the janitor, and they're like, hey, we'd like to talk to you for a minute. And like the first words, I ain't seen Dr. Ford. I don't know what you guys are saying. I haven't seen Dr. Ford. And they're like, well, we weren't planning to ask you that, but it's interesting you mentioned that. So I can't remember their exact reply, but it was like, what's the efficiency of that thing? And it was something like, this isn't free energy. I don't know. I can't remember the exact wording, but no free energy here. I don't know what you're talking about. And so I was just kind of like, all right. It wasn't really what I was getting at. This was a long while ago, but I was kind of like, that's interesting. So this thing is very efficient. If I recall, I think the Japanese started to really take over the steel industry from the U.S. when they began using induction heating to smelt iron. And, they didn't have to haul in all the coal and all the coke, and it's extremely efficient. There was, and I believe there still may be, like a very small niche of induction cookware, induction heating cookware, and that never seemed to go anywhere. But it's like, to heck with that, make the thing a space heater. And now you put up a solar panel and you can heat your house in Michigan in winter. So that's, again, I don't want to draw attention to these people, and maybe it's not as good as I think it is, just from looking at it and noticing it's 75 watts. But that's another example of what you can do when you have a coil and cap in resonance. Well, it's another thing you could do with it in resonance. In previous videos, I talked about making a bipolar commutation circuit using an Arduino, and I actually went through the coding for that. It took me like 2-3 days to figure out. I was an idiot. Well, maybe not an idiot, but it took me a long time to figure out how to do that. But I really wanted to do that because in the back of my mind was always this, that the same logic that I used for the bipolar commutation circuit, switching the input from positive to negative to positive to negative, could be applied here. And so I did a little bit with showing the different effects that different magnets and different coils in a traditional sort of hub motor setup. And there's still a lot that I don't understand there. But certainly it is on the agenda to, instead of pulsing it from the power source, to pulse it from a cap, have it do that, switch it over. And so while I haven't built it, it's always been in the back of my mind that once you have the bipolar commutation down, all of those pulse DC motors should, and I'm going to say should, quotation marks, be able to run 5 times more efficiently. And if you saw what the efficiency was when I was doing it, if I actually mentioned any of that, that would be quite interesting. Now, one of the reasons I say should is that you still have those magnets flying past, and I don't think that that would interfere with the resonance between the cap and the coil. But until you build it, you don't know. But if it didn't work with that, you're not going to get that much interaction with the zero force, and you're not going to get much interaction with a window motor. So you put those in resonance, some or all DC pulse motors should be able to be 5 times or more efficient than what I was showing there. But again, I actually need to do it. It's easy until you start working on it, and it's like, oh, this gets complicated. But that's certainly on a to-do list. So what else? Yeah, here's just a really rough graph of both the voltage change with the discharge cap and what's going on with the cap that you're gathering for a DC converter. And again, I don't trust this data for anything other than just looking at the trends, because what I really want to do is make sure I've lined these two up correctly, and then see if there's any place here where you're flipping negative but you're getting transformation of voltage, because that would be where that would be a nice thing to have. But I think the other approach with the DC-DC converter is just to get as brief a not smudged, a sharp transient pulse as you can get. And then also, that's why I'm saying I want to look at, what's the calculated resistance from the skin effect. I want to put it on an oscilloscope and actually look at the waveform at different places. I guess the other thing I'd mention, you don't see that tremendous swing to the negative unless you have everything optoisolated. When I was showing it earlier, there's a connection to the Arduino ground with BJT or a MOSFET, and that's fine if you're just trying to flat out see how fast you can go. But it really blunts this flipping of the cap to negative, and I think it's just something to do with there's another ground for current to go into, and so you don't get that. But at least that I'll have to look at it again, but it takes time. But that's what I recall. But an SSR is plenty fast enough for a pulse motor, and it would probably be fast enough for one of those induction heaters as well. So I guess I can't really think of anything else. Well, there's other stuff to talk about. I mean, we haven't even talked about different coil shapes and a whole nother video there, but I think this is plenty for this one, and so we'll wrap it up. I'll wrap it up, and just again wish everyone happy holidays and a Merry Christmas and Happy New Year, and stay well, everyone.